Hello, and welcome to this tutorial for BioXTAS RAW. In this tutorial, you will learn how to use RAW to do singular value decomposition to determine the number of components in a SEC-SAXS solution peak. To do this tutorial, you need the RAW tutorial data, which is available on the RAW website. For this tutorial, we're going to use data in the SEC data folder. So I'm going to go ahead and open that up. In particular, we're going to use this phenylalanine hydroxylase dataset, this PHEHC_SEC, which was graciously provided by the Endo group at Cornell University. This is just in a standard raw series save format, the HDF5 file, so you can just double click it or select it and click plot to load it. And you can see it loads up there. Now we're going to go to the series tab. To open the singular value decomposition window, we right click and select SVD. It opens the window and runs an initial SVD on what RAW thinks is an appropriate range of the dataset. So singular value decomposition is essentially just a way of looking at how many different components there are in your dataset, or how many important components there are in your dataset. So what we see on the right, on the top plot, is a plot of the singular values. And one way to kind of look for strong or important components in your data set is to look for how many singular values there are that are above the baseline. In this case, we see that there are clearly 3 singular values above the baseline, which means there are probably 3 strong components in this data set, 3 strong scatterers in the data set. On the bottom plot, we have a plot of the autocorrelation of the left and right singular vectors. So these are vectors derived from the singular value decomposition. You can essentially think of them as scattering profiles for the components in this peak and concentration profiles for the components in this peak, though that isn't quite right. And when we're looking at the autocorrelation, we take one of the singular vectors, we shift it by a point, and we compare it to itself. And so the idea here is, if it's a real component, if it has some kind of physical meaning, if it's a real scattering profile, for example, it ought to be smoothly varying. If you move by 1 point, it ought not to change very much. And so the similarity to itself ought to be high. The autocorrelation should be near 1. If instead it's a component that's essentially just noise, it isn't a strong scattering component in the data set, the autocorrelation will be near 0. So in this case, again, we see there are 3 significant components because there are 3 autocorrelations that are close to 1. My usual cutoff for autocorrelation is somewhere around 0.6 to 0.7 is what I consider a significant component. Combining that with looking at the singular values, you can really narrow in on how many different scattering components there are in your data set. So we can change some other things. We can use unsubtracted or subtracted data. Turns out the data set that we loaded in here, this is already subtracted data, so if I toggle between the two, you'll see no difference. But normally, what you'd see is between the unsubtracted and subtracted data, there's an extra component that comes in when you look at the unsubtracted data that corresponds to the buffer scattering. You can change what range of frames we're using. If we really want to isolate the peak, we could say change this to frame 110. You can see that doesn't really change anything because all the significant scattering components are in this elution peak itself. We can change how many things we're plotting on the right plot here. We can save just the plotted singular values and autocorrelations, or we can save the entire SVD. And once we're done, we can just click OK. So with that, that's the end of the tutorial. You should now know how to use RAW to determine how many components there are in a SEC-SAXS solution profile using singular value decomposition, or SVD.